Hello and welcome to Chapter 1 of Introduction to Earth Science. And you'll notice on the slide there it says 14th edition, and that's fine. The publisher did not release 15th edition slides, so I'm using these, and they'll work perfectly well for the semester. I've reordered all the lectures to make sure they align with or I should say, realigned the videos to the book that we're using this semester. Let's get into it. Earth science is all sciences that seek to understand the Earth, right? And that includes our neighbors in space. So it's not just confined to Earth. We want to understand, take what we've learned from Earth and maybe apply that to other planets as well. And that's what ultimately we're trying to look at. So earth science includes geology, which is literally the study of the earth. You have oceanography, which is the study of the oceans, meteorology, which studies the atmosphere and the processes of weather. And then you have astronomy, which studies the universe. So you can kind of specialize in each one of these. I happen to be into the geology portion of it. But these are all part of Earth science because they all take place on Earth or at least in the solar system or universe. But the processes and the methodologies are still the same, whether you're on Earth or Mars, for example. Now, we also have to look at earth science as an environmental science as well, because there's natural hazards that occur that affect humans. Humans require resources to make and build things, like mine. You'll see the mine there on the left. And we unfortunately also have the negative effects of humans, which is things like air pollution, smog, climate change. Those all play a role. And that's part of what we would call environmental science. But it's still, because it takes place on Earth and it involves Earth's processes, we consider that in Earth science as well. One of the things as a geologist you have to be able to wrap your head around is this idea of geologic time. As humans, we live on average 80 years, we'll say. I don't know. I don't know what the exact number is. Well, Earth is 4.6 billion years old, and that number is really hard to understand. In the book, it says if you started counting the day you were born, it would take you 150 years to count to 1.6 billion. So that's that's a big number, all right? So the idea of recent, what happened recently in Earth's history, is very skewed because we as humans look at it as a human time frame, and we can't do that. So the geologic time scale was developed with sort of these major developments sort of pointed out as divisions. So for example, let me give you an example. 65 million years ago, the dinosaurs went extinct. So that's a major sort of break point in the geologic time scale as in terms of one of those units. And when you start going into geology, it's one of those numbers you just sort of commit to memory and you memorize. So let's take a look at geologic time. If all of geologic time on Earth were a calendar, this is how it would break down. And this is kind of an interesting exercise here. So let's take a look at this first. We have the origin of the Earth at number one here occurring in January 1st. So the first day of the year, the Earth formed, right? So by the end of February, the last day of February, that's where we find the oldest known rocks found here on Earth. That's how old they are. They were formed at the end of what would be the second month of Earth's history. By late March, we finally get some semblance of early life, which is in the form of a bacteria, already like towards the tail end of the third month of this calendar. By mid-November, we start to actually get little critters that have hard parts, right? Like shells, snails and brachiopods and things like that. So we are already 10 and a half months in. We're in the 11th month and we're finally seeing some semblance of life that we might know. Then finally, at the tail end of the 11th month, we get plants and animals that start to develop on land. All right, so we live on land, right? We don't live in the oceans. All anything that was associated with living on land did not form until the very end of November in this calendar. But wait, it gets better. So between December 15th to 26th, this is when dinosaurs dominate. So in the grand scheme of geologic time on Earth, the dinosaurs get about a week and a half worth of prominence. That's it, a week and a half. So now all of the rest of these occur on December 31st in the PM, meaning towards the tail end of the day. So here on December 31st, with 11 minutes to spare in the year, 11 minutes before the end of the year, we finally get humans. So if you didn't feel insignificant before, we have 11 minutes left in the year with all this time, and that's when humans finally occurred. Okay, now here we are with about a minute and 15 seconds left. We have the glaciers, which was about 10,000 years ago. Now, between with 10 to 15 seconds left in the year, we have when Rome ruled the world, so to speak. That's with 10 to 15 seconds left in the year. With only 3 seconds left in the new year, or before the new year, excuse me, before the end of the calendar, with 3 seconds left, that's when Columbus in 1492 sailed the seas, so to speak. Now, you can't really see it because my head's in the way here, but I will explain it on December 31st at 11:59 and 59.999 seconds. So 1/1000th of a second before the calendar end of the year, we have the turn of the millennium or the year 2000. 1/1000th of a second left in this year to account for the 20, and that was already 20 years ago, right? We just had the New Year's, so 21 years ago. 1/1000th of a second. That's it. So the vast majority of this calendar exercise was taken up by the very earliest parts of Earth's history. And again, going all the way back to we didn't even see human life forms until there was 11 minutes to spare at the end of the year. So we're pretty insignificant in the grand scheme of things. Even the dinosaurs didn't get that much time, right? They had a little over a week and a half worth of existence in the span of Earth's history. Pretty crazy stuff. So, scientific inquiry is about asking questions and doing science. People say, how do you do science? Well, this is how you do science. First, you make some sort of very general assumptions about the natural world. The first is that it's consistent. So, the processes that are taking place right now on Earth are the same processes that took place a billion years ago. There's nothing new under the sun, so to speak. The processes are still the same. Erosion takes place the same today as it did a billion years ago. The other thing with that is that it's predictable. Now, let me explain that. Predictable being over long periods of time. Now, I'm going to use earthquakes as an example because that's what I know. So, earthquakes, I can't tell you that there's going to be an earthquake in Los Angeles in the next 1, 10, 15, 20 years. What I can tell you is there'll probably be a major earthquake in the next 5, 10, 15,000 years. Now, on human life scales, that really doesn't help us much. But being that the way the Earth moves and everything, and the plates jostle around, we know that at some point there will be a big earthquake there. It's just I can't tell you it's going to be tomorrow or next year or 10 years from now or 20 years from now, but I know over geologic time it's going to happen because the Earth doesn't stay stagnant. It's always moving. Now, the goal of science is to discover these patterns in nature and use, things like math and observations to predict what's going to happen in the future. And that's always, what you want to try to do is take what you've learned and try to predict what might happen down the road. So, for scientific inquiry, you have this idea.
And that can become a hypothesis, which is a tentative or untested explanation. I think this is doing this because of this. That's my hypothesis. I'm proposing a question out there, and I'm going to make observations and do um, and for test these things in order to prove it right or wrong. Now, a theory is the next step, sort of in that, where it's a theory is a hypothesis that's been tested and confirmed, not by just one person, but by many people, right? You can't just have one person say, well, this worked. That's good. I'm good. Everything's great. It's perfect. It doesn't work that way in the scientific community. You have to have others be able to prove it as well, or otherwise they'll reject it. Then you have what's called a paradigm, which is a theory that explains a large number of interrelated aspects. And the best one of these is the theory of plate tectonics, or the paradigm of plate tectonics. There's lots of interrelated concepts that take place under this sort of umbrella of plate tectonics, including how volcanoes form, how earthquakes form tsunamis. I can go on and on and on. Mountain building, um, ocean crust, subduction zones, all these things all fall under this paradigm because they're all interrelated of plate tectonics. Now, the scientific method is something that was developed to understand and be able to methodically get the job done, so to speak, when it comes to science in a proven way that's reproducible by not just one person, but by many people. And that's done through gathering facts and observations and measurements to help formulate these hypotheses and theories. Now, observation and measurements are done either remotely, like with instruments, or in the field where you actually go out there and take measurements at that particular site. Now, my background is in earthquakes. I run the seismometer. I'm measuring earthquakes 24/7 at UWM, and that's an observation machine, so to speak, where I don't have to sit there and watch it. I can log into that machine anytime I want and see what's going on, but it's always recording. I don't have to go somewhere to record an earthquake. Now, the scientific knowledge is gained through collecting facts. Again, that's an observation, you know, developing a hypothesis is and a lot of times you have this idea, you go out and see if the facts sort of support that hypothesis, then maybe you conduct an analysis or experiments, and then you re-examine that hypothesis. Is it worth producing or pursuing, excuse me? Can you accept that hypothesis? Does it need to be modified, or does it need to be rejected? Is it just not work? And that happens all the time. Now, what a lot of people don't understand who aren't might not be in the sciences is, like, scientists publish papers in these journals. Now, these journals just don't allow anybody to publish. Those are what are called peer-reviewed journals. What that means is when you submit an article to a journal, they give it to three, four, five people that you have no idea who they are. They're anonymous, and they read through your paper to make sure the science was done correctly. Okay, and so I've been through that process. I've had a paper published, and I had to make revisions. They didn't like some of the things that were in there, and I had to make a few revisions, and that's completely normal. That's part of the process because everybody wants the science done correctly. Now, theories need to be able to withstand this examination. If you're going to create a theory on something, it needs to be able to be held up to scrutiny. And then sometimes you have totally unexpected occurrences where, you might get a result you have no idea why you got it or whatever. And that's where this sort of reproducible science needs to be in place. Just because I got it to work doesn't mean everybody else can get it to work. And that's if that's the case. And I've seen this in the world of seismology where somebody will publish a paper and somebody goes, eh, and then they might check up on that, go, I didn't get those numbers. I did it exactly the way you said. What's going on? And this happens in a lot of science where people
in the scientific community sometimes overgeneralize or over make too many assumptions to the point where nobody else can reproduce it because there's just no way unless that exact uh, environment is recreated, and that's a difficult thing to do. Let's switch gears here a little bit. We're going to look at the early evolution of Earth. So the origin of the Earth, most researchers believe, was formed along with the other planets roughly at the same time. So we're talking 4 to 5 billion years ago. So there's this thing called the nebular theory. Again, it's a theory. It has, um, but a lot of the evidence points towards it. So that's why they call it a theory, that it evolved from an enormous rotating cloud called a solar nebula. And I'll show you an image of this in a minute. The nebula was composed mostly of hydrogen and helium, which makes sense. Those are the lightest elements. They're the most abundant elements in the universe. And without getting deep into the chemistry, that that's where a lot of the other elements are derived from, based because they collide with each other. Now, the nebula theory says that about 5 billion years ago, it began to contract. So it's spinning, spinning, and it starts to smush itself, so to speak, and flatten out. So it smushes and flattens out into a disk shape with sort of this pre-sun in the middle at the center. It's not the sun that we know today. It's like a proto-sun. The inner planets begin to form, and then the outer planets begin to form. So here's an image of this, taking a look at this. So here we have this huge nebular cloud out here, which begins to spin and spin and spin and sort of flatten itself out, which makes sense because of forces that, when something's spinning, and that's typically what happens. Now, what then you have sort of these concentric rings here, and you can see those made up of all kinds of little rocky bits of debris, and a lot of those start to slam into each other and create the planets that we know in their current orbits. So, if we got you go to the third orbit away here, and here's Earth's orbit. So whatever was in this particular ring here is what happened. That's when they all start to smush together and coalesce into this rocky glob that then becomes Earth eventually. Now, as Earth formed, you have these heated radioactive elements and heat from high velocity impacts, and the temperature starts to increase. Then the heavier metals, things like iron and nickel, begin to melt, and because they're denser, they sink to the center, leaving the lighter compounds and components to kind of float on the outside. That's where you get what we call differentiation. So you have this, and that's what we have now on Earth. You have this solid core and sort of this molten mantle and thin outer crust, which are much lighter materials. Then you have the gaseous materials that escaped out into what would become sort of this primitive atmosphere. There's more to it, the atmosphere being created than that, but that's where it first starts, is you have these gases that are created with this ball that's been smushed and starting to rotate and getting slammed into. Now, Earth has several spheres to it. Once the Earth formed, it kind of created these concentric spheres. Now, one of those spheres is called the hydrosphere, which is the ocean. It's the most predominant feature of the hydrosphere because 90%, or excuse me, 71% of Earth's surface is water, right? And 90% of all of the Earth's water is in the ocean. 97% of that water, of the water all over Earth, is in the ocean, which really sucks because you can't drink ocean water. So it's really not available to humans. Now, the rest includes fresh water and lakes and streams and glaciers and groundwater, and I'll show you an image of that in a second. So the vast majority of the Earth's surface and the Earth's water are contained in the oceans. So here's an image showing you sort of the breakdown of where the water is found on Earth. And you can see the oceans are made up of 96.5 of all of the water on Earth currently. And 97.44 of all of the water on Earth is salt water. So there's other water in addition to what's in the ocean that's salty. All right. So that leaves a whole 2.56 uh, of fresh water left. And of that 2.56, 1.76 of that is locked up in glaciers, leaving only 0.77% for groundwater and even less for surface water. So even though we live right next to the Great Lakes region here, these and Lake Michigan is huge. It's not even the biggest one, but it's a big lake, right? So combining all of the surface water in streams, lakes, and soil moisture accounts for only 3/100ths of a percent of Earth's water that's readily available to us on the surface. And then groundwater is only 1% of the Earth's available water. So combined, we have 1.003 of amount of water available to humans. Um, that's not a lot of water. You can get into other facets of, making sure we keep those waters clean and everything because we need them in order to survive on Earth. Another one of Earth's spheres is the atmosphere, which is, the air that we breathe in. Without it, we'd be we'd all be dead. So here in this image, I want to look at my other screen. We have the Earth's surface here, and then we have the troposphere here. And you can see with the graph a little bit that 90% of all of the atmosphere lies below 10 miles. Okay, so that's crazy. It's about here. And that that just shows you how thin the atmosphere actually is. We also have the biosphere, which includes all life, like living plants, animals, critters, whatever. And it's concentrated near the surface, whether it be on the surface or in the ocean. Um, and this is what biologists and ecologists deal with, but it's a huge part of you know life on Earth. You can't have one without the other. We need the trees to sequester the carbon dioxide to produce oxygen, which gives us an atmosphere and something to breathe. So we need the trees, for example. We need all of the life. We need things to eat and grow, and so the biosphere, while not technically what we're looking at in this particular class, is hugely important as well. Then you have the geosphere, which is the solid Earth itself. It extends from the surface to the center of the planet, and it's the largest of the Earth's four spheres because the atmosphere is super thin, right? You have the hydrosphere, which can be deep. The ocean can get very deep, but compared to the actual radius of the Earth, it's nothing. So, and then you have the biosphere, which is just, again, it's a thin layer on the top of the surface of life. So the geosphere comprises the bulk majority of all of those four spheres, just based on the fact that the Earth's radius is so big. Now we have the solid Earth, which is based on compositional differences. It consists of the crust, the mantle, and the core. And we'll discuss those a bit as we go along. So the divisions are um, based upon how materials behave. Are they solid? Are they sort of a plastic in nature? Are they molten? And we'll take a look at those. So here's Earth, and we have the hydrosphere, which is the liquid part here, the ocean. We have the atmosphere, which is, obviously the thin layer of gas that we breathe. Now we can look at uh, the layering by physical properties. I'm going to look at my other screen here. So the layers on the left are based on things like solid, liquid, or weak. Are they weak or strong? So we have the lithosphere, which is all of the crust and the upper mantle. All right. And that's typically rigid. What we call the lithosphere, excuse me, is fairly rigid. That's where earthquakes occur. Okay. Then we have this thing called the asthenosphere, which is solid but mobile. And what we mean by that is it can be pretty warm, but it can still move. And that's where we believe a lot of the sort of the crust is right along, moving along this between here and this sort of transition zone. So that's where we think the plates are moving along because it's molten enough to allow the plates to move. And then over here we have layering by chemical composition, and the, excuse me, I'm trying to erase this here. The cross section shows that there are three main layers: the crust, the mantle, and the core. There's an inner and outer core, but we're just looking at the three main divisions: the very thin outer crust, the very thick middle mantle, and then the core of the of Earth. So the crust is this relatively thin, rocky outer skin, and it is, in grand scheme of things, it's very thin compared to the rest of the Earth. You have continental crust, which is less dense, and it's granitic, so a lot of granites. And you could think of that as almost like it's buoyant, like it floats, and I'm using that term loosely. It floats on top. So when you have in plate tectonics, we have what are called subduction zones, where you have one plate diving beneath another plate. The plate that's diving is almost always the oceanic plate, which is dense and mostly basaltic rock, because it sinks faster. Now there are areas of the world where you have one oceanic plate diving beneath another oceanic plate, and that's again based on subtle differences or just pure, like, brute force of the plate moving. Like, for example, the Pacific plate is going diving beneath the North American plate and Eurasian plate way up in the Alaskan island, the Aleutian Islands and up in Alaska. So that's where you have one oceanic plate diving beneath another oceanic plate. So there are the oceanic plates have a tendency to be dense and sink faster. You have the solid outer rocky shell of the mantle. The mantle comprises 82% of Earth's volume, so it's by far the largest portion of Earth's interior. You have the upper mantle, which is the lithosphere that I mentioned earlier. Then you have the relatively soft layer, which is the asthenosphere, and then you have the very hot lower mantle. Now, the lithosphere is the combination of sort of the upper mantle and the crust. And again, going back to what I mentioned earlier, this is where this sort of the plates are sort of the boundaries of the plates, and they're riding sort of over the asthenosphere. Excuse me, it's hard to say. Um, which is sort of a plasticky layer that almost acts like a conveyor belt. Then you have the core, which is divided up into the outer core and the inner core. The outer core is a liquid layer. Now, when we say liquid, we don't mean like watery liquid, but it's molten enough to act like a liquid, which generates Earth's magnetic field. That's where we get that from. And then you have the very solid inner core. The temperatures and pressures are such that the very inner core of the Earth is solid. And we know these types of things based upon indirect measurements from things like geophysics, which is what I went into. Gravity measurements and earthquake measurements and all of these things play a role in understanding how what the interior Earth is doing without actually having to go there. Now, plate tectonics is that paradigm I mentioned that states that the Earth's lithosphere is broken into big slabs or plates that are always in motion. Now, they get stuck from here and there, stuck, temporarily, where it may be moving slower, but the plates in general are always moving because there's molten heat at the center of the Earth that's always driving those forces to make the plates move. So the Earth has major and some minor lithospheric plates. You have where we are here, the North American plate. You have the South American plate, the African plate, Eurasian plate, and these are all moving in different directions relative to each other. And these plate movements are what generate most of the big activity that you see on Earth. Things like earthquakes, volcanoes, mountain chains, tsunamis. All of these things are being driven by the movement of these plates. Now they move slowly. They're not moving super fast. The fastest moving plate is the same speed as roughly what your fingernails grow at. But they do move, and because of that, like I mentioned, you get things like earthquakes and volcanic eruptions. Now, there's three types of plate boundaries that you can have. You can have divergent plate boundaries where you have plates that are being pulled apart, and then new Earth is being pushed up underneath it. And those are the youngest rocks on Earth. They're sort of just born. They, the plates move apart, new Earth is formed. They move apart some more new Earth, and you get the idea. Then you have convergent plate boundaries where you have two plates slamming into each other. Most of the time, that's subduction, where you have one diving beneath another, and I've already mentioned that a couple times here. You also have continent collisions, like, for example, India slammed into Eurasia, forming the Himalaya Mountains. So India just came in and brutally just smashed into it over millions of years, pushing up the Himalayan mountains. And then finally, you have the transform faults, which are areas where plates just sort of slide past one another. In a motion, they just slide like this back and forth, or not back and forth, but in a specific direction. And the most common example of that you might know about is the San Andreas Fault in California. So the San Andreas Fault represents a plate boundary between the North American plate and the Pacific plate, and in that particular area, they're actually sliding past one another. They're not diving beneath each other. They're not being pulled apart. They're just sort of sliding past one another. So here's sort of a cartoon version of this. You have this sinking plate here. This is subduction taking place where that plate's going back down into the mantle. And in doing so, you create heat like this here, which generates volcanoes and mountain ranges. And then here we have an upwelling of heat from the bottom, which comes up here, comes out, and goes in each direction that way, creating new plates, or excuse me, new rocks, and pushing the plates apart. So wherever there's something being born, something sort of being killed, if you want to look at it that way, born and died. And so plates are born in divergent boundaries and they go to die in subduction zones. It's just that the subduction zones are areas that are at much higher risk for things like the really large earthquakes, the sevens, eights, and nines, and then the volcanic eruptions and the tsunamis and things like that. So that's where sort of all the action is. Uh, and also most of the divergent plate boundaries on Earth are in the ocean and don't affect anybody. There are some that do, like for example, Iceland sits right on the mid-Atlantic ridge and is being pulled apart. Now, if you take the Earth as a whole and you like step way back, it looks like a round ball, a smooth round ball. Now we know there's mountain ranges and we know there's valleys and hills and all that. But if you take it from a global relief, so to speak, you might have seen one of these. I have one at work where you have a globe, and then when you feel it, you can feel all the different irregularities on the surface of the Earth. And even the Himalayas at that scale are just a slightly bigger bump than everything else. So, for all intents and purposes, the Earth is flat, when you look at it as a whole Earth. And the continents are made up of those granitic rocks. Now, the ocean basins are on average 2.8 miles below sea level. That's that's like 10 to 8, 9 to 11,000 feet deep. That's the average. That's how deep the oceans are, and they're made up of basaltic rocks, which are denser and heavier materials than the continental rocks that I mentioned earlier. You have um, some of the major features of continents are mountain belts, or like the Alps, the Himalayas, the Chilean mountains, things like that, the Rocky Mountains. You also have the stable sort of interior of continents, shields, which are extensive areas where you have very, very old rocks, very hard rocks, like the Canadian Shield or the Australian Shield, which is where some of the oldest rocks on Earth have been found. Then you have stable prop platforms, which are, deformed rocks covered by sedimentary rocks. We'll cover a lot of this later on in the semester. There's a chapter on all of these things. So here's an example. You have the Canadian Shield up here. The- These areas in red are very, very super old rocks. Some are more than 4 billion years old. You have old mountain ranges. So the Appalachian Mountains out in eastern U.S., that mountain range is over 480 million years old. So it's been weathered down and eroded. So that's why they're not as tall as, let's say, the Rockies, which are younger, or in an extreme case, the Himalayas here, which are the tallest mountains in the world, and they're still being actively pushed up. I just read a couple weeks ago that they took some new measurements with satellite technology and things like that, and they found out that in fact the Himalayas or Mount Everest, the tallest mountain in the world, Mount Everest, actually got taller. So some of the major features for the ocean basins are the continental margins. Again, we're going to cover all this in gory detail. They have their own chapter later in the semester, but we're just going to kind of gloss over this. Things like the continental shelf, which is when you get off just offshore, it's a slow, very slow. It kind of mimics the shoreline, but it's just a very slow, gentle shelf, and then it gets to the continental slope, which is sort of the end of that, and it steeply drops off. And then you have the continental rise, which is sort of this gradual uplifting. Once you get past the slope, that's where all of the sediments that kind of flow down the slope accumulate. You also have the deep ocean basins, which are, the flattest, the abyssal plains, which are the flattest places on Earth. The deep ocean trenches, which are the deepest portions on Earth. So, for example, in the Marianas Trench, there's a place called the Challenger Deep, which is over 29,000 feet deep, the deepest place on Earth. And then you have submerged volcanic features like seamounts, which are just islands that either eroded to the point where they're under the ocean again, or islands that were formed from beneath but just never made it to the surface. You have the oceanic ridge, which is the mid-ocean ridge, includes both the mid-Atlantic and the East Pacific rise. It's the largest continuous mountain belt in the world that spans about 22,000 miles and is almost all completely underwater. And is it's made up of many layers of igneous rocks that just sort of pile on top of each other over millions of years, because that's where the new Earth was being created, and they kind of pile on each other, creating these ridges, what we call the mid-ocean ridge. They can get quite tall. They're not the Himalayas, but they can get quite tall. Now, Earth as a system. So when we look at Earth, you can't just look at one facet of it and go, "Yeah, I understand it now." Earth is a complete system, which makes it both fun to study but also very complicated because there's many facets that go into trying to understand it from all of those spheres we talked about. How does the hydrosphere interact with the biosphere, with the atmosphere, the geosphere? How do they all interact with each other? So when you're looking at earth science, you can't not look at it as a system, um, because it all plays a role. How does mining, which is a man-made activity, um, influence the hydrosphere? There's typically a lot of water pollution that's associated with mines. So there's interactions there. Now, this makes it very complex, and that's one of the things that makes like climate change so complex is because you have zillions of variables over a planet-wide range. So, a lot of people think, well, just because my weather is this, well, that's not necessarily what climate change is. I don't understand everything with climate change. I'd be lying if I said I did. But I'm just trying to show you that it's a much more complicated problem than just looking at a rock in a microscope, so to speak. Um, Especially when it comes to the big processes. Now, Earth as a system it's an open system because there's things flowing into it, there's flowing out of it, kind of like a river system, as opposed to a closed system like an automobile cooling system where it kind of rotates through, Gets hot, gets cold, gets hot, gets cold, gets hot, and it's just flowing through there in a closed system. Earth is definitely an open system there because there's things that flow in and out of each one of the spheres all the time, depending on what's going on. Now, Earth as a whole system consists of almost an endless array of subsystems. And we're going to talk about a few of these over the course of the semester. The hydrologic cycle, which is the water cycle. There's a whole chapter on the water. Um, and then the rock cycle, what happens with rocks, as they they're created, they get deformed, and then they erode, and how do you get sedimentary rocks out of igneous and metamorphic rocks, things like that. So there's all kinds of subsystems that are taking place that play a role in this much larger system. Okay, and finally, you can't talk about Earth as a system without talking about what drives these processes. And the sun is the external one, right? Without the sun, we don't have an atmosphere, we don't have weather, we don't have wind, we don't have a lot of things. It's not warm enough to sustain life on Earth. So the sun is it's obviously a huge portion of the external sources of energy. And then you have Earth's interior, because Earth has a heated interior, which allows is a big part of why we have life on Earth, because without the heated interior, we wouldn't have things like volcanoes, which played a role in developing Earth's atmosphere. So between the sun and then the heated interior, you got to have both for life to be able to occur on this planet. And then obviously humans are a part of the Earth system too, because we manipulate things. We change things, we harvest, we mine, we drive cars. All of these things play a role in this much larger system. All right, so that's going to do it for chapter one. I hope you enjoyed that. It's kind of a fun overview. We're going to look at a lot more of those things in depth. In fact, there's a chapter for geologic time, there's a chapter for oceans, there's a chapter for the hydrologic cycle, there's a chapter for the rocks, rocks and minerals. So there's a chapter for almost every concept that we touched on in this chapter. So, all right, I'll see you on the next one.